Okay, in your book on page 136, if you're watching the video, find your book, find page 136. You'll see there we have 10 postulates. Okay, there is a mathematical genius from Greece named Euclid. Back 2,000-3,000 years, I don't even know when he was a long time ago. Alright, anyway, he invented geometry. In fact, his geometry is called Euclidean geometry because he invented it. And the way he invented geometry is he came up with a list of 10 postulates. Postulates are statements of fact that don't have to be proven. That don't have to be proven. That people just accept as fact. Alright? So it basically, his geometry is based on you believing these 10 things without any kind of argument to them. Alright? In the future, beyond Euclid's years, through time, many other mathematicians started debating some of these. Postulate 5 is the most popular one to debate. The one that says through any line at any point not on the line, there's exactly one line parallel to that line given. Right? That seems to make sense. If I were to draw that picture, here's a line, here's a point not on the line. And I'm going to draw a parallel line to that line through that point, right? So that's what I'm given. And what Euclid said is there's only one parallel line through that point. There it is. And some of these other guys say, no, there's more than one. All right? What Euclid's doing is he's considering a plane, where some of these other guys think about spheres. A line on a sphere is actually curved, so you can create a lot of parallel lines through that. But again, we're going to be doing Euclidean stuff here. So his postulates are going to be fact. All right? 2 points determine a straight line. So if you have 2 points, there's only one line that can go through it. All right, unique meaning one. Straight line extends indefinitely far in either direction. So in other words, if you have a line, it goes all the way that way, all the way that way. The arrows demonstrate a continuous line. Even though you're only seeing part of it, the arrows demonstrate that they go on forever. A circle may be drawn with any given center and a given radius. So if you know a circle has a specific point where it starts, its center, and it is a radius, let's say, of 4, there's a circle. Radius of 6, circle. Radius of 2, circle. Alright, so circles are possible. If you know the radius and the center, you can make a circle. Alright, number 4, all right angles are equal. How big is a right angle? 90 degrees. Does 90 equal 90?
Yeah.
That's the postulates, that's what they are. They state facts, everybody knows they're true, but he's basically making the law of geometry here. These 10 things are true, we're going to go from there. I already talked about 5. Things equal to the same thing are equal to each other. Watch this. What does 2 plus 2 equal?
4.
I said we weren't going to do that today. 2 plus 2 equals 4. What does 1 plus 3 equal?
4.
So if 2 plus 2 equals 4 and 1 plus 3 equals 4, then 2 plus 2 obviously has to equal 1 plus 3.
Yeah.
Okay. Things equal to the same thing are equal to each other. Right? If x equals 2y plus 7 and x equals 4y minus 1, then 2y plus 7 equals 4y minus 1. You might recognize that as substitution. We've already done that this year. Things equal to the same thing are equal to each other. If equals be added to equals, the sums are equal. Okay. They had weird language in Greece back in the day. 2x minus 3 equals 6. If equals be added to equals, the sums are equal. Are these equal?
What?
This thing and this thing, they're equal? Because it says they're equal, right?
Yeah.
Does 3 equal 3?
Yeah.
So if I add equals 3, add equals to equals, the sums are equal. Addition property of equality. He invented that, or at least he wrote it down first. All right. If equals be subtracted from equals, remainders are equal. Same idea, except this says plus 3. Now this says minus 3. So then you get 2x equals 3. Subtraction property of equality. Okay. And honestly, in algebra, those are equal. They're the same. Add a negative. You know, it's the same as subtraction. Figures that can be made to coincide are equal. So, in other words, if you have some triangle and another triangle right next to each other with the same angle measures, same side measures, those triangles are congruent. All right, and the whole is greater than any part. If I take 5, and that's the whole, and the parts are 2 and what? 3. 2 and 3 are less than 5.
Yes.
Whole of anything is greater than any part. All right. So, getting on to proof. All right. When you do a Euclidean geometry class, which you're not doing Euclidean geometry in this school, we do geometry or trigonometry, which has some geometry in it, a lot of trigonometry in it, but it's more of a pre-calculus class. All right. We deal with proof in this class, which we're going to do a few proofs, not a lot. A Euclidean geometry class, you have about 15 of these a day, every day for the whole year. You're welcome. We're going to do a few. You're going to know what a proof is, you're going to know how to do a proof, but we're not going to make you guys get writer's cramp and stuff. I enjoyed proofs in high school, but I was one of few that did. Like in my class of 124, I think one person in our high school liked proofs. Guilty. All right. And my belief with math is I'm not going to make you do stuff that you completely hate, even though it seems like I make you do that. Trust me, what we're doing does not compare to these things. You don't like these at all. All right. Anyway, now that I've said my piece on that, if you like proof, I can give you more, but let me know. All right. I want to prove angle y equals angle z, and all I've got in my possession is these postulates, along with some things we've already learned this year, some properties we learned, okay? The property we're trying to prove is the vertical angles are equal. That's what we're trying to prove here. All right, vertical angles are equal. We already know that, okay? But we're not allowed to use something we already know to prove something we're trying to prove, all right? So we've got to use everything else we know to do that, all right? So obviously they're equal because of vertical angles, but that's what we're trying to prove, all right? I'm given two lines that intersect, and y and z are the angles that I care about. X and p are some other angles I can just look at if I want to. Okay, I may or may not need to use x and p. I need to use facts in order to prove that that y and z are equal to each other. All right, so here's my first fact. That's a straight line, right? Would everybody agree, since that's a straight line, x and y are equal to 180 degrees?
Yes.
Because they're a linear pair, they add up to 180. So my first statement is going to be measure of angle x plus measure of angle y is equal to 180 degrees. What I'm doing with my statements in a good proof, if I'm trying to prove something equals something else, I want to first create some equations with those pieces. This says y equals z. Here's an equation containing y in it. Okay? If I can get y and z together at the same time, that's great. Can't always do that. There's nothing right now that can get y and z together based on things other than the vertical angle rule that I'm trying to prove, so I can't do that. So I at least have one equation containing angle y, so now I need an equation containing angle z. What would we think on that one? I could say p and z add up to 180 also, right? All right. But that's not good because y is what I want, x is what I have, right? So what I want to do is I want to create another equation with x and z hopefully together.
X and z.
Very good. And if we take a look at the other line there, we got angle x and angle z make that straight line. So I can also say measure of angle x plus measure of angle z is equal to 180 degrees. If I'm using the same reason for several things, you can list those several things. The reason for both of those is 180 degrees in a straight line. All right? So again, you state a fact and then you justify it with some mathematical reason. Okay? The reason proof is used a lot in math to teach math is because it puts your brain at a higher thinking level. So when you're doing these, you're having to really rack your brain to really think about what the rules are and how things are related to each other, that kind of stuff. So they are challenging but useful in their challenge. But again, I find the frustration level is not worth the extra understanding in my experience. Number 2.
Do we have to fill in all the...
Not necessarily.
Okay.
I mean, I put 5 boxes just, I think we can probably get this probably done in 4 maybe, but I had proofs in college that there were paragraph proofs. You had to write out like a little story about it that took a page and a half, 2 pages. When you get to the page and a half part, you get to circular reasoning, but basically you're stating something you've already stated before, That's bad. That's like, oh my gosh, I just worked an hour on this thing and I got to redo it because it's not even right. That's the frustration level that you're going to hit. So these aren't going to be that bad. You're looking at 4 or 5 steps probably at most on all the proofs we're going to do. We're probably going to do like 5 or 6 altogether. Okay. So looking at our postulate list, can anybody see a postulate 1 through 10 that might be useful to get y and z into the same equation? Okay, right now y is in this equation, z is in that equation. I need them to be in the same equation in order to get y equals z to ever happen. So can anybody see anything in that whole list there?
What are they called again?
Postulates?
Postulate 6.
Postulate 6, very good. Things equal to the same thing or equal to each other. Notice, x plus y equals 180, x plus z equals 180. Things equal to the same things are equal to each other. So Braden figured that out really well. Angle x and y have to be equal to angle x and z. And this little m in front of the angle symbol is measure of angle. That's just good symbolic geometry there. So m angle x means measure of angle x. Alright? The usefulness of that step in the proof, we're trying to prove this to be true. We went from x in one equation, z in a different, or sorry, y in one equation, z in a different equation, into y and z into the same equation. Alright? It's not what we want yet, but at least they're in the same equation, and that will be postulate 6. If you want to write things equal to the same thing or equal to each other, that's fine. If you want to write postulate 6, that's fine. For the most part, you can be doing these on homework. You're going to get maybe 1 or 2 proofs on tests throughout the course of the year. So you want to remember what that postulate 6 is. That one's used a lot. Whenever you're trying to prove an equation, postulate 6 usually shows up. Number 3. What's the problem with that green equation? We're trying to get y equals z. What's in there that we don't want to be in there? X is in there. We want x to go away. How can we make x go away?
Postulate 8.
Postulate 8. We don't want x. I want to subtract x from both sides. Postulate 8 tells me very clearly, if equals be subtracted from equals, the remainders are equal. Angle x equals angle x, so I can subtract x from both sides. So minus, I'm going to put minus m angle x minus m angle x. Alright? That's what step 3 is. I'm subtracting angle x from both sides of the equation. As Braden said, that is postulate 8. Alright? And then, all I'm going to do in statement 4 is I'm going to carry out that subtraction. Angle x minus angle x cancels, leaving with measure of angle y. Angle x minus angle x here cancels, leaving with measure of angle z. And I'm just going to put down simplified as my reason for that. Anytime you do any kind of algebraic simplification, just put down I simplified it. I'll believe you. And notice, using not the vertical angle rule, but just using other rules that we know to be true, we were able to prove without a doubt, every time we see that picture, those vertical angles are equal to each other. We could have just as easily said angle x and angle p, x plus z and z plus p, they're both equal, subtract the angle z's, and then you get x equals p. Alright, so that's the purpose of proof, is to prove stuff to be true. This right here is a theorem, the vertical angle theorem. Theorems are stuff that are proved with other things, where postulates are just statements of fact that everybody believes. A theorem is something that you can say, hey, this is true, and here's my proof for why it's true. And there you go. There's my proof for why it's true. So that's a theorem, and again, postulates. There's also what's called axioms. Axioms and postulates, for the most part, are the same thing. So, but if you get to do a proof, that's how you do it. On the homework, it might say prove angle y equals angle z, give the picture. It might say prove vertical angles are equal, then you draw your own picture. You make up your own letters, A, B, C, D if you want. You pick out what the vertical angles are, and then you go through the proof of how to do it. All right.